Hello, everyone. Welcome to another problem at graduate level calculus/analysis. Today, we have somewhat surprising result, which claims that there cannot be too many disjoint balls in a Euclidean space. Specifically, it says, suppose B alpha alpha from a index set is a collection of mutually disjoint balls in Rn, in the sense that B alpha intersection B alpha prime is empty. Prove that gamma is finite or countable. So before I prove it, as usual, I want to tell you why this is actually true. So initially you may think that, well, if this is my Rn, in this case R2, I can begin by one ball and then I can go a tinier ball and then an even tinier one. Even between these empty spaces, I want to place other tiny balls, and who is stopping me from having as many as I wish just by shrinking the diameters? Well, the answer is, so fix a box anywhere, a finite box. Okay, there you go. Then the question is, how many balls of radius or diameter bigger than a certain threshold can you place in there? So how many balls, number of balls with a radius bigger than a threshold? Then the answer becomes obvious, because they have to be disjoint. There is no overlap. There is some finite bound on them. And then if you have only finitely many within this square, then there are also finitely many inside the bigger square. And even this square has only finitely many of those inside it. And the whole Euclidean space has then accountably many, at most, balls of radius bigger than A. So what about the balls that can be tinier? That was the problem. Then you go, okay, first you look at A equal 1, and then you look at A equal 1/2. So how many balls of radius 1/2 can you fit into a square? Again, it's finite, maybe more balls, but it is still finite. A equal 1/3, same story, and so on. And then you realize that any ball that we have, its radius, which is some positive r, will be bigger than 1n at some point. And that will be counted in this collection that we considered here. So ultimately, you have countable union of countables, and the whole gamma becomes countable. So that's the basic idea. So you want to put some bound from below, and then also you want to look at one square at a time. So let's see how we can work this out in detail. As always, as important as finding the proofs is to actually how you present them. Because oftentimes I see many students struggling with this part. So they have the idea, they have some sketch of a proof, but they just cannot put them together into a rigorous proof. And that is what I have promised to give you every time. So a difference between a proof and just an idea is the rigor. So what we do, so keep in mind that the proof is just presenting the previous sketch using clear notation and precise language. So for n, a natural number, we define gamma n to be those indices in gamma such that the corresponding ball, B alpha, has volume. Here we're talking n-dimensional volume, so if you were in R2, this will be just area. So has volume bigger than or equal to 1/n. then obviously gamma is union of gamma n goes 1 to infinity. Again, because if you pick any b alpha, it has some volume, so its volume will be some quantity v, and this quantity will be bigger than many of the 1n's, in fact. But if it is just bigger than a particular n0, then this alpha will belong to gamma n0. So that's why gamma is contained in this union. Of course, the other direction is just definition, because each gamma n is picked from gamma. So that's it, and you have gamma a countable union of gamma n. So to prove gamma is countable, it suffices to show each, redundant word there, but to emphasize, each gamma n is countable. Okay, now gamma n are those balls with volume at least 1 over n. And then we go into the box length. So for j in natural numbers, consider the following n-dimensional cube. So you go negative j, positive j, that's the interval from negative j to j, multiplied n many times with itself. So the n-dimensional cube. In R2, it's just a square. Now, claim, the heart of the story, is that only finitely many alpha gamma n exist such that the ball corresponding to this is contained in my negative j to power n. So that's the claim, and the proof of the claim is exactly the picture I showed you. I'm going to, of course, write down the rigorous proof, but the idea is this is a square with finite volume, and then these b alpha are those that are completely contained inside my square. And each one of them has volume at least 1 over n. And so there cannot be too many of them. So by disjointness, if we have n many of such balls, then sum of volume of balls, well, all of them are included and completely contained within the square, and you have no overlap, so this will be less than the volume of negative j to power n. Okay, this guy, the sum of the volume of balls will be n many times each one of them by choice of gamma n has volume at least 1 over n, right? So it could be even bigger, but anyway, this is less than or equal to sum of volumes of balls, and that is less than or equal to, so what is the volume of this thing? It's 2j to power n. And from that, so n is less than or equal to n times 2j to power n. So in particular, actually, the only part we are interested about here is that it's finite. So how many balls of volume at least 1 over n can fit into negative j to j to power n? That's the answer. So it is finite. Now, gamma n is union of alpha in gamma n, such that we could introduce more notation, but it's just easier to write it down. So union of alpha in gamma n such that B alpha is contained in negative j to power n. So probably I could make it better by saying that this gamma n is union over j of these things. So you vary your j, which means you look at bigger and bigger squares, and each one has finitely many of the elements from gamma n, and finally you have countable union of finite sets as a result. So let's make it a complete sentence. Since gamma n is equal to that, we have gamma n countable. And that ends our proof, because previously we said if we show it, then gamma itself is countable. So let me erase my pictures, because I claim that this is a complete proof with all the details. But it was important to see where it comes from. If you read this proof without any picture and motivation, it can be really confusing. And that's what I'm trying to avoid in these videos. So if you liked my video and my solution, please like and subscribe to our channel. And if you have any questions, please put them in comment, because I do read them and respond. Thank you so much. See you in a future video soon.